So today we are going to cover two things. So the first hour we are going to go through scientific plotting with Matplotlib. And in the second part I will go through how you can use a visualization software called ParaView together with Python to generate data for it. And also I will cover the user interface of that application as well. So we'll start with the basics. So Matplotlib is a plotting library that has been developed for integrating with multiple libraries. So when it started, it was kind of first for NumPy, but today you can use Matplotlib with multiple libraries such as NumPy, SciPy, Pandas, and it also integrates directly into Jupyter Notebooks and also in interactive Python prompts like IPython. So the idea today here, I don't want to go too deep here, but you should master the fundamental plotting concepts. Also, we go in a bit how you can create publication quality figures, how you can combine multiple diagrams in a single layout, and visualize data in a scientific way. So we don't go too deep in this text here. So let's start here how you use it. So usually if you install the large Anaconda installation, Matplotlib is kind of built in. Otherwise, it's you install it with conda install Matplotlib. And then the convention to use it is to import matplotlib .pyplot as PLT. So Matplotlib consists of multiple, so it's not only a simple interface to plotting it, there is also a low-level drawing library, which is called only Matplotlib. But we will mostly focus on the Matplotlib PyPlot, which implements a simplified interface to the plotting routines. If you are working in a notebook, you can add this directive here to make sure that the plots are plotted inline in the graphics of your notebook. There's some other configuration options here as well. Let's do this. And you can see here I'm running NumPy 2.02 and Matplotlib version 3.10. And we're using the backend used for the notebook plotting. There's also a way of I'm going a bit quick into a lot of the settings here, but one good idea is to define your own style for how your plots want to be, and you can store them in a large configuration files like this. It's like a dictionary where you set a lot of parameters, and then you plot RC params update, and then those parameters will be used in all your plots, and that could be a good idea. So Matplotlib consists of multiple layers, and there is a backend. So Matplotlib can be run on many different platforms. So you can run it in the notebook like we are doing here. We can run it standalone in a normal Python script. It will open a window, and it can also use multiple different rendering backends. So there is a ag backend. Qt background. We'll go for Qt in the coming lectures, and multiple more different backends. And those are responsible for actually drawing in certain contexts, in Windows or in the Mac user interface library. On top of the backend, there is something called the artist layer, which we will not use in this course. But this is the low-level interface for all the drawing primitives that Matplotlib uses. And the PyPlot here, that is layer on top of the artist layer that implements a lot of functionality in a more easy to use way, and that uses the artist layers for actually implementing the drawing itself. In my last course, I used an even more simple interface for drawing, but have upgraded my slides here to use the object-oriented interface of Matplot or the PyPlot library, which gives you a bit more flexibility when plotting. So there is also very simple functions for plotting which you can also use, but I will show you how you can do it in a bit more flexible way, because you know a bit about object orientation now from the last lecture. So here, the idea here is that when you plot, you create two objects or two or more objects using the subplots command. And it returns you a figure object, which is the window or the complete drawing area like the paper. And the figure you can also use that to save your file, save your drawing to a file. Then you also get an axis object, and that is the actual object that you use for plotting. And here you can see here I can design here how big figure I want. I give that as the first parameter to the subplots command. And then I use, to do the plotting, I use the axis object here to perform the plotting. And all the settings will be stored in that axis object. So plot here will just plot these two series here. And Matplotlib is not constrained to using only NumPy. Anything that can be represented as a list type object can be used for giving it input as series. So in this case here you can see we have two just normal lists of numbers. And then also here you can see I can set different attributes to my object. X label, which is the label on the x-axis, Y label, and title. So you can see here that I get a plot like this. Now it's running inside the notebook. But if you have run this as a standalone script, it will appear in a window, just like it does in MATLAB. Yeah, I'll skip that. Yeah, then also there is it could be also good to make sure that when you're plotting that you actually check your data before you're plotting for errors, so that you don't plot anything that is not valid. And this is an example here that you can create your own function here that takes data here, and then you make sure that the data is not, for example, that the x data is not different from the y data in the lengths if you're plotting line plots. And then you call your plot routines inside a function here, add some additional variables, and then here you return the figure and axis objects just like the subplot command. And then you can run it like this. You create your data sets and your function, and then you pass them along to your function, which will actually plot the function. Okay, I didn't define my function. This. Yeah, so things that you need to check before plotting is make sure that you don't have a not a number in your data, none, empty strings, infinite values, array dimension mismatches. So if you have series you want to plot, you need to make sure that the series are the same lengths. Mixed numeric and string data, for example, yeah, scale problems. So customizing your plot. One thing you kind of is a common task is to create coordinate arrays in different ways. So usually you have to have x-axis, you want to plot a function. You are tempted to use the arange function in NumPy, but there is a better way which guarantees you that you get the starting point and the end point in your x range. So in this case here, you use the linspace command instead, and then you give a starting point, end point, and the number of points you want inside your x series. And then we can use the fact that if you have NumPy, you can use the sign function here to compute sign for all x values and return that into our y array. And this is a way you can quickly plot out the x and min values. So to create professional plots, we use the object-oriented way again. So we give it a size, we get our figure object and our axis object, and then we do our plotting here. And you can do in different ways here. So one option you can do a lot of things directly in the plot command. So here you can give line width, you can do labels, you can do alpha here is transparency. But you can also do labels here in the, like separate methods here, calling them as on the object. You can also set legend, for example. You can set if you want to have a grid, and if the grid should be an alpha, transparent, semi-transparent. You can also use horizontal line here, axis horizontal line, to indicate certain interesting things here, for example. So here I want to mark the y equals to 0, x equals to pi divided by 2. We can also set limits on the axis here using the set lim and y lim. And then we can also have, if you want to have custom tick marks, you can do that as well. So in this case here I have give the x values for the ticks, and then I can actually do my own labels here. And it takes Unicode character as well, so you can plot them as well. And then you do set x ticks. That is the actual values that you want to show on the x-axis, and then the labels. Tight layout is adjust the layout so it when all the plotting is done, it makes sure that you have the correct margins and it's packed together in a nice way. So let's run this. So here you can see we have our own tick labels here. Here you can also see these dashed lines here are the different marker lines that you can have to indicate things in your plot. You can also customize the styles of the drawing, and that you can do using special format strings. And those are, for example, colors are the letter R, J for green, B for blue, K for black, C for cyan. And I think these are taken from the MATLAB plotting functions as well. You can combine them with, for example, if you want a red ring, you can do RO, green square with GS, and then you can combine these markers in different ways. You can also add line style, so single line is a solid line, 2 dashes is a dashed line, dotted, and dash dot. And here we can see here, I'm going to plot here a red circle for XY here. And then you can see here I do a blue circle solid line. So you can see red circles here. And here you have the line with the different series that you have the dash here. That means that you have a line as well. I could have done RO dash like this, and then you get lines between those as well. And if I can do also dash dash here, and then I get dashed lines here. So this is how you can combine the drawings. And here you can also see a feature here. We have no, it's not a feature here. We have 2 plots here. These are separate plots after each other. And I said before, you can specify most of the parameters directly in the plot directly here. And you can also add more. You can do both, but usually this is the more using it on the objects here is easier to read and easier to kind of modify, because you see exactly what you do here. Here you have to kind of browse inside and you have a really long command line argument. Let's see. So if you want to plot multiple series in a single diagram, it's always a good idea to have one of the coordinate arrays that you kind of that is the same for all the series, and then you vary the series here, for example, y1, y2. And you can also, if you want smoother curve, you can in the linspace here you can very easily just add more points, then you get a smoother curve. And here you can do, for example, here if you create your plot here, if you do multiple AX plots, they will be added on top of each other. So in this case here, I have one series here with Y1, which is red, line style dash. I have a label here, and I have Y2, that is color blue. So those will be plotted in the same diagram in this way. You can also do more sophisticated, if you want to plot multiple plots in a single diagram. You can have subplots here. You can see there are the first parameters is the number of rows and number of columns. So you have 2 rows, 1 column with a figure size 10.8. Then I get 2 axis objects back from the plot command. And the first one is the top one, and the second one is the lower one. You can do the same thing here. If you do 1.2, then it's the other way around. So then you have 1 row, 2 columns. So let's see how that can look. So here you see I have 2 plots on top of each other. And then I can have 2 plots next to each other here by doing subplots 1 row, 2 columns. Yeah, important also is that when you are plotting for publication, you need to produce figures that have a higher resolution, at least 300 dpi, and you should also perhaps select some of the vector formats if you can't produce high enough images. So it's like PDF, EPS, SVG, and Matplotlib supports most of these. Also, when you do colors, you may need to think about people are colorblind. So you need to make they should be distinguishable in both grayscale and for color and color. And also the figure should be readable when you reduce them to a column. So you need to kind of have the font size with enough size. Yeah, and the visual design principle, you should, everything you have on a plot should serve a purpose. Also, try to be consistent when you're doing multiple plots, so they look the same styling. And as I said, accessibility is also important. Colors for colorblind readers. Do not clutter your plots too much. Honest representation, of course, without misleading and visual effects. That's also important. So a single panel publication figure here. I have this is kind of fake data here. We invented. So here is we create a subplot here, single column width, and then we have a scatter plot. And then we plot the three-headed curve. So you can see here that we can add different plot types here in a single diagram. We also set the font sizes here. We define everything here. We add a legend, and we add some text. Now you see here you can also use math notation in the plots. So it's also possible to use LaTeX notation in your plots if you need it. And you add a $sign, and then you can add your math notation inside. So this here you see that you have some constant here, and you have clear labels. You have clearly marked legend here with different data, and you have font sizes that are clearly visible. Now we just go through some of the specialized plots. So the plotting function, the default one is for plotting 2D lines and dots, but you can also do, you have seen some here, these dots here are the scatter plot. But you can also do histograms, for example. That is the hist function of the axis object. It looks like this. You can set the number of bins, and then you can plot the bars. There is the scatter plot here that you can put the points here. You can also control the alpha values of the individual scatter objects. So if I put, for example, 0.3 here, you will see that they're more transparent. So one is completely opaque, and 0 is completely transparent. You can do bar charts using the X bar. You can also have error bars in these plots. You can do contour plots, and here you need to first create the lean space in X direction and the lean space in Y direction, and you combine that to a mesh grid object. And that you can use to calculate the function, that's the C values here, by giving the X and Y grids coordinates here. And then you can use, in this case, we can have a contour that is filled, so that is contour F, this one here. And then you have contour, which is just the contour lines. And we combine them into two different plots in here. So 1 row, 2 columns. And we have our axis 1 and axis 2. You can see we use them here. And you can see we get them next to each other because we said 1 row, 2 columns. You can do 3D plots as well. Use the same mesh grid as before here, and then you can get 3-dimensional plots here. And I think we have an alpha value here. We can do it 1.0. No, it's still a bit transparent. I think that is an artifact. Yeah. Then we have a bit larger example here in climate analysis. So this part here is just data that has been generated. I generated with an AI here to kind of illustrate this. And then same thing here. We can have subplots here, 2 rows, 1 column. We get 2 axis objects here that we use. Fill between, so a time series with uncertainty, and then we add a plot, moving average here, and then we do axis 1 plot here as well, normal plot, multiple series, moving years, trend line, add a legend, grid, transparent, and we indicate some points here on the Y axis here. Yeah, and then so it's a long example here, but you can see you can do quite advanced stuff with it. So you get these here, and you can see also we color the bars here in different colors. My recommendation here is that perhaps make functions. So if you want to use figures, put them in functions, because you can see it becomes quite complicated at some point with all the settings for your plots. So it could be a good idea to kind of combine them and to be able to reuse the same kind of plot multiple times. So instead of doing everything in a single script, you create a function that takes the data as input and then produces the plot. There are some other ways here, but there's another example. You can skip that. But so just kind of how you can run Matplotlib to summarize. So object-oriented approach is that you use the subplots command to get the figure and the axis object. There is an old style you can do it as well, which just do plot x, y, plot x label. And that has been, we are moving away from that because it contains a lot of global state, which we don't want. In the case of the subplots command, the axis object is the state. It contains the states of your plot. In this case here, there is a hidden state that is used, and sometimes it can it clashes with each other if you have multiple plots. So in this case here, you get a standalone figure object and a standard axis object which you plot on, and all the settings goes into these objects. If you do another figure, you have different objects and a different state. You can also do explicit parameter settings. So instead of doing this, there is an order of the parameters here. Use these keyword arguments here. This makes it much more clear what you actually mean with the plot, instead of doing this. Because then the user that reads your code has to figure out which is the third parameter here. Yeah, validate, and the good idea always to print the data in some way so you can see what goes into your plots. Use professional formatting. So to be able to use these plots in publications, you need to work a bit with this to try to see what font sizes work, and tweak these parameters so you get a nice plot. Let's see here. Yeah, just quickly here. I will go through too detailed here, but you can use Matplotlib together with pandas. And pandas, I will finish my lecture on that as well, which is a toolkit for processing data, tabular data, not array data that we have in NumPy, but tabular data. And you can do, there is a when you have a data frame, you can do def plot, and that uses Matplotlib to do the plotting. Sometimes also, if you have large data sets, you can reduce the memory footprint of a plot, you can use rasterized here, and then it stores the plot as an image instead. And finally, when you want to write your plots to disk, you can use the save fig. So the figure object is the canvas, the paper you plot on, and then you use save fig to write it to disk. And here you can specify, for example, format here. If you have an extension of PDF, it will write PDF. You can set the resolution of your image and how you want the bounding box to be. If it should be some margin or it should be close, you can control that as well. It can save as PNG, SVG, and also JPEG. So if we run this here, I think we should be able to have a PNG file here of the plot. So if you want work publication, you need to use the figure, the save fig commands here. And you can also define your own custom styles here. Just like we did beginning, the custom settings, you can do a dictionary that specifies certain parameters, and then you can give that in the plot style context here using the with statement. And then if you create your plots here, all of them will have those same styles. So that was what I wanted to talk a bit about on Matplotlib. There is a web page on which I will show you, which is really nice. So if you want to visualize something, instead of kind of figuring out which command to call, go to the Matplotlib homepage. There is a examples section here. And it's like a gallery here. So you can see here, there is an image for each of these diagrams here. And if you see, okay, I want to do these bar charts here, then you get the code here that you can use. So if you have an idea what you want to plot, just go in here and browse here to find kind of what looks like the diagram you want, and then just click on it, and then it gives you the code. It's really nice. So before kind of struggling, can be a good idea to kind of just see if there's something here that fits what I want to plot. There's also documentation here on there's a user's guide here that goes through also the different interfaces of Matplotlib, the artist interface and also the PyPlot interface. So it's a quite advanced toolkit for plotting. So let's continue along. So the next part I wanted to talk about is, I think I will start this. So next I will talk a bit about a tool that is for visualization that is a bit more if you have more complex data. So what I want to talk now is the ParaView application. We are currently up with version 6, so this is a bit older slide, but I think it's a good introduction to ParaView. So ParaView is a visualization application that kind of is a Swiss Army knife for visualization. You can take most any data, open it, and do a lot of different visualization techniques. So I will go through some of the stuff here in the slides, but then I will switch over to the application and then demonstrate the application without the slides. Yeah, what is it? It's an open source scalable multi-platform visualization application. It has support for distributed visualization as well, so you can actually open really large data sets by running it on multiple nodes, so it can scale. It has a very intuitive user interface. It's complicated, but when you learn it, you kind of see the flow, but it has some. There's a lot of controls, but I will show it later. It's extensible, so basically it has a kind of plugging architecture. So all the visualization algorithms are provided as plugins. These are some examples of what you can do with ParaView. So these are really large-scale visualizations in CFD, but you can also do chemistry, mechanics, most data sets. It can handle really large set of data here. Now it's starting to get a bit old here, but 6.3 billion unstructured cells you can do if you want. It's built upon multiple libraries. So if you start from the bottom here, you can see it builds upon OpenGL and MPI. That is the main libraries. So OpenGL for graphics, so it will do hardware accelerated graphics. MPI, that is when you want to run large visualizations. You can run them on multiple nodes, so you can use MPI for communication. The really important stuff happens in the next layer. That is the VTK layer, and that is the visualization toolkit. And that is a visualization library written in C++ that contains almost all scientific visualization algorithms in a single toolkit. On top of that, there is something called ParaView Server, which is, if you run it in parallel, that is more important. Then you have a server side, which you use a client to communicate with. You will never see this when you run ParaView standalone, because the ParaView client will automatically start up a ParaView server. It's built in, so it's just if you want to scale it up, you need to use a server. The user interface is implemented in Qt, which we'll also go through in this course. Interesting thing here is also it has a built-in Python interpreter. So when you implement visualization, you can actually save it as a Python file, and then you can run that Python file to recreate the visualization again. So it can save the state of the visualization as Python. And you can see also that there is a PV Python here. That is a Python interpreter that has all the libraries from ParaView built in. So it comes with the application. Let's skip that as well. So it's a really large, its funding is from multiple American national labs. So it's continuously developed. And as the current version is 6.0. So what is visualization? So we already started with matplotlib here, going from series of data, functions, numbers to a graphic representation. So when you have done your simulation, you have arrays of data, but you need to kind of make them comprehensible in certain ways. So visualization is going from numbers to something that you can interpret with your eyes. ParaView supports many different data structures or data types. You have, starting from top here, you have the uniform rectilinear grid. That is grid data that has the same distance from each point. Then you have a non-uniform rectilinear grid. Then you can specify the distances between different points in the grid. You could have a curved linear, and you can have polygonal data structures, which are like finite element meshes and that kind of data. And you can have completely unstructured grids. Depending on which kind of data structures certain visualization algorithms can be used. For certain unstructured grid, you have a more limited set of algorithms. If you go for the uniform rectilinear grid, you have a lot of different algorithms to use. There's a lot of data on the paraview.org site. There is a user's guide. There is a lot of tutorials that give you example how to use ParaView. So I will go to the application now. So this is the ParaView application. It has, like a normal application, you have a menu structure here on top. You have open here, you have different options here. These are if you have data that is time dependent, you can move through data with these controls. View controls. But the important stuff happens on the left side here. This is what's called a pipeline browser. So what you are going to create in ParaView is a flow, data flow. So you start with the input data, and then you add filters or plugins that create the visualization for you. And everything you build here will have properties in this part here. And we'll start here. So first we will create data from sources that are artificial. So for example here, in the sources section here, we can go into geometric shapes here, and we will do a sphere like this. And now we created a sphere, but you can see here that nothing happens. And that is a design feature of ParaView, because in many cases the data is so huge that you can't visualize it directly. You need to do some operations on it before you want to visualize it. But if you load something into the visualization flow, you can see here that the button apply turns green. And when you press that, it will actually generate the visualization here. But before that, you can change your parameters here if you want. If you press apply, you can see I get the sphere here. And the sphere can be, you can change the properties here. So theta resolution is how many node points it should, the resolution of the sphere. And what you can do here is also you can change the representation here. So now it's a solid sphere, but here on top here you can change the representation of your sphere. So for example, we can do surface with edges, and here you can see the actual geometry construction here. So you can see it consists of triangles, and we can change here. For example, we do 16. And now you see, as soon as I change something, you can see the button turns green again. That indicates that your data is not current in your view. So then you have to press apply again, and you can see here that it's increased resolution of your sphere here. You can also visualize, for example, here points. So then you see only the points of your sphere. You can see outline. That is the bounding box of your data. But surface is the common one. You can also do wireframe like this to see the structure without the rendering, the surface rendering. This most common one. What you can also do is that you can Go down here. Now you can see here I have a solid color, and that is because my sphere doesn't contain any data to visualize. It's basically just a sphere. The only thing we can select is the normals here, and that is the normals that control the lighting here. But when you load your own data, you will see first solid color, and if you click down there, you will see the data sets. I will come to that later. We can change the color here, press edit, and then we can do a red sphere like this. Changes the color. You can make the object transparent. Difficult to see. You can do so that it looks a bit more plasticky. That's basically it. You can of course also change the radius here, like then it gets larger, and then you have to zoom out here. If your object isn't too large like this, you can click here on top here to do zoom to data, and it will zoom out. There's also reset your viewpoint. There are also other things that you can change which side you are viewing the object from. So that is sphere. What you want to do next is kind of apply some modifications to your data. And one thing we can do with the sphere here is we can apply a filter. So the sources are the data that you bring into the application, and then you can apply filters to the object here. So we can see we can do, and there is a lot of them. You can see the menu kind of fills my screen. So sometimes common ones here, the ones also on the tool set here, there are a lot of different things you can do here. So there is a lot of filters you can apply. I think, and you can do, one thing I usually do is I go into the search part here. So if you do control space, you will get a search box. And here you can search for, I can do shrink, like this. And then I click this one here. And you can see here it added shrink to my workflow. And the shrink factor here is, it will take every triangle or surface in the model and shrink it by a certain factor. And that can be something useful if you want to see how the structure is built up and where the data is. And then press apply. And then you can see here that it shrank the triangles. You can also see it changed the color. That's because it created a new object, and that is kind of standalone from the other object. So here you can do a green here, like that. We can also do a scale. Okay. Transform. So, you can add a transform to the object, and you can see here that I can do translation, I can do rotation, I can do scaling. So I can do, for example, let's scale it 1 point. And then I apply that. Then I can also option here, I don't want to see that box. So now I scale the object, and you can see here that I have a flow here. I started with a sphere, I shrank the triangles, and I applied a transform. You can see every time I do it, it turns off the other objects here. And that is optional. You can actually turn them on again. So let's turn on our sphere. Now the sphere appears inside here. What we can do then is we can go into transform here, and we go down to representation here. We do opacity, like this. So in this way you can combine different visualization together and highlight different fields. And you can also do, you can for example add an axis grid here, so you can see how big your object here is automatically. So let's take a 10-minute break, and then I will continue with some more advanced examples. So now we used synthetic data. ParaView doesn't have its own data type like Word, where you can save it as a document. So when you're done with this, you do use the reset button here. That will reset the visualization and empty the pipeline. So what I will do now is I will open a demonstration file. Let's see here. Examples. So now I loaded the data file, and you can see here that on the lower side here now I have more things here. I have different data fields. So the dots here are data points that are attached in the outside positions of the to the nodes. You could also have data connected to the cells. They look something like, and this is surface here, but you have a cell as well. I will go through that when I go when I do the Python thing. So let's look at this data here. So press apply. Now you can see here I have a cylinder of some sort, and the idea here is that this hole here, that is a heater. So there is a heater connected to this inner surface here, and by default it doesn't show you any. It has, if you go down here to coloring, it says solid color. We can change here to visualize other fields here. So for example, temperature. We'll visualize the temperature in this here. It's a bit problematic here because we can't see inside of this. So I set temperature here. So what I want to do is I want to be able to look inside here. So I want to make a cut of this data structure. If you look on top here, you can see some standard filters. You have this one called clip. There is something called clip with planes, and there is an extract cell. There is generate glyphs. There is a warp. No, sorry, that is a vector field, sorry. And then there's a warp here. And what we can do to kind of look inside, we can use the clip here. And then you can see here that I get some kind of thingy here, and that is a clipping plane. In the properties here, you can see here that you can specify the origin of clip plane and also the normal of that clip plane. You can switch the clip planes here quickly by using X, Y, and Z. But let's keep it in X direction. There's also an option to get the camera normal if you want to clip it in the orientation of the camera, but let's keep it a bit simple here. It's also possible to, you can rotate it here manually. That was not what I wanted. You can drag it here by selecting it like this. So you can interactively move the plane, but you can also control it here by specifying the origin here, 0, 0, 0. And then I press apply. You can see it clipped on this direction here. If I specify, for example, -1 here, it clips on the other side. If you're done with if you're happy with this, you can do uncheck the show plane here, and then it will remove this. Doesn't show the interactive doohickey here anymore. So what you can do here, for example, if I want to show the outline of the entire object, I can switch on the top level eye here, Now you see here that it's completely filled again. Let's change the surface here to just a solid color, and then we do put it opacity down here. So now, or we can combine it. This was really not what I wanted, but and you can combine. So here you can see that you can see the surface outline here as well. But we can close that for the moment. So what we would like to do here as well is to, this data set actually contains a vector field. So we can actually visualize the vector field as well. And what we are going to do then is we are going to do a glyph visualization. And glyphs will place markers where we have vectors and orient those markers towards the vectors. So what we are going to do is we are going to, now I'm selecting here. If I would select here, I will only place markers in the clipped volume. I want to use the entire volume here. So I will go back to this part here. I will turn off that for the moment, turn on that. And we will make that a bit more transparent, like this. And then I will do glyph. Then you can go, let's see here, properties here. You can select which glyph type here. We can have arrows. What we also have to select is an orientation array. So we need to orient our glyphs into some vector. So if we click here, you can see I only have one because it detected the only data structure that has vectors in it is the V field. So let's select that, and we should scale it towards the velocity here as well. You can see also there is a button here with two arrows here. That is an auto scaling here. So if I press that, it will try to auto scale it depending on the magnitude mode. Then you can also select where you should place the glyphs. So one option is to place it at all points. But the default is actually we kind of space them equally in the bounds of the volume. You can also select how many sample points should be used. So let's try it here. So now you can see here, if I zoom in, you can see I have arrows that represent the velocity field here in my volume. But it's kind of hard to see, so perhaps we should color them in some way. So if we go down here, coloring, let's color them by the velocity. So then you can see also that we get a scaling array legend here that shows you 0 to 22 degrees, or 22, the magnitude of vectors here. We can also use something else. So if you have a lot of vectors, it's probably unreasonable to use these 3D representations here. You can also use lines. Then we get something like this. Perhaps we should have a bit less transparency here. So what we can do here, if we do, for example, 1,000 here, you can see here that we have, it only places lines every 1,000 times here. So that is glyphs. What we also can do when we have a vector field is we can use streamlines. So we can release streamlines inside our field and then follow the flow inside a volume here. So go back to the main volume here. Let's turn off the glyphs here, and then we use streamlines here. And by default, it will use a line to release the streamlines, but in this case, I think we need something that is more a sphere. So here you can select point cloud, and then we do it a bit bigger. Like that. And then we can select how many streamlines we want. So 100, we will reach 100 points. Maximum streamline length, we do an auto here. Vectors is the V field here, we only have that to select from, and then we do apply. So now you can see here we got streamlines in our module. Oh. I put what I can do more here, so if I want to illustrate or visualize them a bit better way, I can color them, of course, with a speed, the vector magnitude. But if I want them to be a bit thicker, I can apply another filter on top of this. So in this case, I do filter, and then I do tube. And this one has number of sides is the number of sides in the section that we want to kind of extrude on the line that we have here. So we keep it to 6, perhaps a bit bigger. Apply. Now you can see here that I draw tubes around these flow lines a bit too much, perhaps, like this. You can also vary them by, for example, if I want to vector, you can have them a bit different thickness depending on, for example, different scalar values, for example. So when you're done with your visualization here, I'm happy with this. You can save this in different ways. So one way of doing it is using save state. Then we just do let's do test. So default is PVSM as the extension. That is a built-in format for ParaView. And then I do reset here to reset the visualization. I open load state, test PVSM. Now it asks you to, because the state file contains the file names of the data sets that you used. And you can choose file names. You can also use the file names from the state. You can also search for the files in a specified directory. So let's hope that they are inside here. Seems to work. Now you can see here it recreated the entire flow again from your data set. So it doesn't just reads your data files again and applies your visualization again. And it also saves all the visualization settings here, which view you had. What you can also do is that you can do save state, change the file time to a Python file. We'll do test here as well. Okay. Now we just make sure, okay. Then we go to the desktop here. So now you can see here that it generated a ParaView script, which can be executed by the PV-Python interpreter. And you can see it uses some modules here that are specific for ParaView. And here you can see the object-oriented structure here that it generates for your code. And what I can do here, let's see if I can run it on the command line. I think I ran it with the wrong version of ParaView, so let's see if we do it this way. Python. Yeah, then you have to add this interact here, so otherwise it just runs the simulation and returns again. And so let's save this. So now you can see I have my visualization, but no user interface in this case. So this is one way of kind of quickly, you can also save the image here to an image file as well. So in this way, you can quickly reproduce your visualization states. So let's go back. So that is how you can use ParaView in general way. So what I'm going to show you here as well today is how you can generate input files to ParaView. So if you look here, if you can open here, you can see here that ParaView supports a lot of data files. But it also supports the VTK files. Let's see here, VTK. It's called star VTK, and I think there's a lot of different built-in types here, but you can generate files that you can read with ParaView. So let's reset here and go back to Python. So there is a special module that is called PyVTK. And that is not a wrapper for the visualization toolkit, but it's a special Python module that can generate the data files needed to do visualization in ParaView. As I said before, VTK supports different kinds of data, grids, structured grids, unstructured plots, polygonal data, unstructured grids. So you can install PyVTK by using pip install PyVTK. So we'll do that. So the first thing I will do here is so you can use it here by using from PyVTK import star. You can also do import PyVTK as VTK, and then you do prefix vtk.polydata here. So in this case here, you define your data structure in the classes that are provided by the PyVTK module. So in this case here, I have polydata. That is kind of a general data structure. Here you provide points, the coordinates, and the polygons. So this is a topology here. So this is a polygon going from points 1, 0, 1, 2, and 3. Let's define that. Then you can attach data to the geometry. And you can attach scalars, you can attach vectors, and you can attach them to the points at the nodes, but also to the cells. So let's create some scalar data here. So I have point data, and here I just give a list of different values for each of the points in the polydata structure. And then you can combine this, or you can also create cell data. And that is, here you can attach scalars to the cell data. So in this case, the cell data are these polygons. And for each of the polygons, we attach scalar values, normals, and more data. So let's create that. And then we have created this data structure. You can combine them together to VTK files. So here you create VTK, so VTK data. You provide a structure, which is the thing we created in the beginning, so the geometry. You attach the point data and the cell data. And then we can do VTK2 file, either as ASCII, so it's a text-based file format, or as a binary VTK file. So running this, we can look here, we have one that's called example1 VTK. So let's download that one. And then we go back to PowerView, open. Then we go to downloads, example1, open. So usually when I do new data, I try to kind of just press apply here to see what data we get. Now you can see we get a cube here. So the poly data was apparently a cube-like geometry. We can do the surface with edges. You can see the data here. We can also see what data is plotted. So you can see it uses the sample data here. And sample data was attached to the points. So you can see our legend here goes from 0 to 7, which is consistent with what we have here, data from 0 to 7, and we call it sample scalars. So the names here, you can specify pi data is important because that is also what you can see in PowerView. So in PowerView, you can see here that we have sample scalars, we have cell normals, cell scalars, and so on. All the things that we created are visible in PowerView. So coloring here is from that. We can also color here, so let's see, cell scalars. We also provided from 0 to 5 here. Let's see if we can go back here. Scalars 0 to 5, and we call it cell scalars. Those are attached to the surfaces. So in this case here, one color per surface here. This is the polygon, and we gave it one color. And there are some other things here as well, but the normals here, those are the normals that defines the lighting things as well. But so this is how you can go from Python to PowerView. I will give you some more advanced examples. So we do reset here again. We can also create structured points. So in this case, we do grid 3 by 4 by 6, and then we just provide point data here for each of the points in the grid here, and we save that to the file. So now it's shown outline, so surface with edges. You can see here I have 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. And we can go scalars here, and you can see here that it's just filled it with the values we provided in our script. What you can also do is reuse the structure here. So we have a structure here that we defined in this VTK structure. We can load example2 again as a file, and then we can reuse the structure and then provide a function here to calculate the values in the grid points. And then we get the other one. SP. You see we put the function in here, and then it calculates the function depending on x, y, and z coordinates. So here we have a set of points, we have a set of vectors that we attach to points. Then we create an unstructured grid consisting of points with attached vectors. And we have hexahedrons, tetrahedron, polygons, triangles, strips, quads, triangles, and so on. So we can combine them here, different kind of geometry, add them together to create an unstructured grid. And if we download that one here, can open that in ParaView. Do a reset again. Yes. Here you can see we have a mixture of different, it's hard to see, but there is actually a line here. So if we do a wireframe, you can see there is a line here. And different data structures combined together. We can color by vectors, scalars. We can also do a glyph here to illustrate the vectors that's here. So you can see you have vector zeros, scalar, we scale them to vectors, scalar magnitude, and then we apply. So you can see here there's a vector field attached to each point of the data set. So the final part here I want to show is that how you load different kind of data and combine them into ParaView. So in this case here I have a data structure that looks like this. It has a header file that says that it has the data structure X, Y, and Z and U, V, V. So these are velocities. And then you can also see that we have a grid here that is 96, 65, 48. And then you have all the data coming in like this. So what we can do then, we can use the NumPy feature called load text to load that data set. And because we know that there are 2 header rows, we can tell the load text to skip 2 rows. So by using this here, we can ask it to jump over the first 2 lines because we don't need them anyway. Then we need to convert this into points and vectors. In this case here, the points are extracted from this X, Y, Z, U, V, W. And we extract the first 3 columns, that is the points. The last 3 columns are the vectors. And here is one of the disadvantages with PyVTK is that you need to convert those to lists. So we use the 2 lists here to convert to list-like data structures. We create point data here with our vectors. We name it the vector1 set. We create the structured grid, and you can see here 96 by 65 by 48. We give that as input. We attach our points and the point data. And then we write this to file, and we should get a uvw.vtk file. And then we can open that, we download that to our desktop, like that, and then we go into here, we do a reset again, yes, and then we open, and we download, should be a uvvtk file, open, apply. So let's just check what we have here. So surface with edges looks like this. So you can see here it's thinner at the top and thinner at the bottom here. We can do surface, and then we just plot the vector field here, the magnitude. So you can see there is some kind of flow going on here. So let's try to do a streamline here. Yep, okay. We select point cloud. Let's see here if we can. I think we need to make this a bit more transparent so we see. Make this one a bit bigger. Yeah. Nice. Let's do apply. So you can see here that it streamlines, like we can perhaps make it a bit 1.5. So to be able to see them better, we can do we close the sphere, and we can use the tube filter. So this way we can see the flow lines through this data set. So we went through from a purely text-based table to three-dimensional visualization of flows here. Yes. Let's see, we have the final one as well. The final illustration here, and then I will stop here. So I will download elevation datasets. So basically, it's a binary file with height information and a really simple data structure. It has a header file in binary that is 268 bytes long. So we need to skip that before we read into here. So we open the dataset here, which is called, or rather, it's a binary file. So we do RB. We seek, which is we jump over a certain number of bytes. And then we go MP from file. This is a way of reading a binary file to a NumPy array. And we need to specify that the data is stored as unsigned bytes in the array. So we give that, and then we get unsigned array, NumPy array with unsigned bytes. We do just plot it here to show how it looks, and then we do point data, scalars of the X field here, and then we know that the height field is 400 by 400 pixels. So let's run this. So you can see this is a representation of a height field, and then we got an error again. So let's run this in my other application here. Okay, let's see what it's supposed to export. So let's do a reset and load that one again. So now we've got 2D data in here, so we can't actually rotate it. So we need to convert this to a three-dimensional plane, and we need to kind of extract the height information and apply that in 3D. So what we can do then, if we can use warp, so we go into filters, warp by scalar, like that. We select the scalar field, which is a scalar 8 field here. We can do, let's start with some scaling factor here. We apply, and we get the height field here. What we can also do here is to, so you can see here, if we zoom in here, it looks kind of faceted here. And that is because the lighting information is calculated in the triangle middle. So it has the same surface on top. What we can do is we can create vertex normals. The first thing we do, we create a surface to this, and then we create surface normals. And you can see here that it's smoothen out the surface here a bit. What we can do here as well, we can change the color mappings here. We can change to something that is more different color scale. And to make it even cooler, we can do it more like plasticky. So now we went from a 400 by 400 image to a height field visualization here. We can also do contouring. That was not my filters. Not that one. That was about that one. This one should be. So you can see we added surface contour lines here on the surface as well. So this way you can build your visualization going from the elevation data down to the contour surfaces here. And you can save it as a Python file and rerun it again if you want. That was what I wanted to show today. Sorry for the errors here. I thought there's something in the Google Colab I need to check.